Well, welcome back, everybody. Let's talk about some more specific spaces. The one I want to discuss a little bit are H2, Bergman space, sometimes related A2, sometimes B2, depending on the taste on the author, and more importantly, the Dirichlet space. In all of these spaces, all of them are RKHS. In all of them, they are defined on the open unit disk. And at each point, there are functions which are not zero at that point. Therefore, for every z in D, we are sure that kz is not equal to 0. In all cases, case H2, I mean, I don't use different notation, but in H2, A2, and D, kz is not equal to 0. So we immediately deduce that if F is a multiplier, doesn't matter for which space, then the absolute value of F at point Z is majorized by the norm of the multiplier for any Z in D. So, and since in each case, 1 is in this space, 1 is in H2, 1 is in A2, and 1 is also in the Dirichlet space, we conclude that the multiplier space, they are not the same. In each case, they are different. But in each case, the multiplier of the space, let's say multiplier of the space X, we will mix with this X, multiplier of H is inside in H. In all cases. And therefore, note that H is also sits in hole D, so they are holomorphic functions. In this case, there is, I mean, no danger to say that the multiplier of each space is in H infinity. They are analytic and also bounded. So in each case, for the Hardy, for Dirichlet, and for the Bergman, they are bounded functions. Naturally, we ask, do we have equality? And this is a point where the type of the representation we consider is important. If you remember, I mean, I don't know if you were in my lectures in July about Hardy spaces. I gave 4 or 5 equivalent definitions for H2. And not all of them are good here. For example, if we stay with the definition by coefficients, F is in H2 if it has the series representation with coefficients which are square summable. And now you want to show that every element of H infinity is also a multiplier. So you need to consider an F, which is, I mean, in H infinity, you don't have a specific information about its coefficient, except that H infinity by itself is also in H2, so something like this holds, but it doesn't help that much. And G is in H2, and then you do the multiplication. and this is a holomorphic function, it has its own Taylor representation. You have to find the coefficients of this and show that the coefficients are a square summable to conclude that it's in H2. Well, it's not a good method to do it. So here we stick to another representation, so another definition. Equivalent definition of H2. The norm of an element f in H2 squared was defined to be integral from 0 to p f r e to the I theta squared d theta divided by 2p. And here either you take limit or supremum, they are the same in this case, between 0 and 1. So functions such that this quantity is finite, it's in this space H2. And now it's easy to show that easy now. I have to say now, easy to show that H infinity is in multiplier space of H2. Because if F is in H infinity and G is in H2, then integral from 0 to pi f r e to the I theta g r e to the I theta squared, we replace f here by the largest possible value. So it's less than or equal to the norm infinity squared, 0 to pi gr e to the I theta squared. And then take the supremum with respect to r. So sup 0 to pi f r e to the I theta gr e to the I theta squared d theta 2 pi less than or equal to supremum here over integral of g. And this supremum is the norm of g in H2 squared. We have norm of f infinity squared. And this, by definition, is the norm of fg into squared. So, in short, norm of fg in H2 is less than or equal to norm infinity of f norm of g in H2. Conclusion is that f is in the multiplier algebra of H2, and moreover, the norm of MF is bounded by the norm of f in H infinity. But we already know the other way around. So we already know the same thing bigger than or equal to that. So conclusion is that the multiplier algebra of H2 is precisely equal to H infinity. And moreover, for every element of that algebra, the norm coincides with H infinity norm. Very interesting result. And I invite you to do the same type of calculation in the space A2, in the Bergman space. The only difference is that instead of doing integral over t, we do integral over d. We do integral over d. It's a two-dimensional integral, but the rest is the same. And indeed, all the calculation I did here you can modify it a little bit and replace the integral from 0 to pi by integral over d, and pretty much do the same thing up to the end and conclude that the multiplier algebra of A2 is also H infinity with the same norm. That's good. So it's I add here A2 and we obtain the same thing. But interestingly enough, the story for D is different. For the Dirichlet space is different. Of course, the multiplier algebra of D is inside H infinity, also inside D. So it's inside the intersection, and also what happened? And also we know that for any F is in no, not this D, the other D. In mult D, norm F infinity is less than or equal to norm F in M. We know that based on the general theory that we developed before. And in the previous two cases, indeed, when we do the intersection of, say, for example, H2 with H infinity is H infinity. But here it's not the case. It's a bit smaller. So I mean, you can imagine like that. This is D, this is H infinity, and this is the, intersection. And this intersection by itself is an algebra. I mean, D intersection H infinity is an algebra. This is very easy to show. And we naturally wonder, is it the multiplier algebra? I want to show that this is not the case. Indeed, the multiplier algebra is smaller. Is inside, but smaller. So this is mult D. And to show that this is smaller, I do it, in the, straightforward case. I give you an element, an F here, which is in the intersection H infinity, but it is not a multiplier. Very, very direct proof. So theorem. This color. There exists an element F in the intersection H infinity such that F is not an element of multiplier D. Just a matter of thinking, finding the right Taylor coefficient for the function F, and to show that it satisfies the required properties. And this is done before. Forgot who did this, but I have the answer. Proof. For the definition of F, I do it this way. F of Z is defined by a Taylor series. But the coefficient an are defined in this way. A highly lacunary series, lacunary sequence nk is defined to be 2 exponent 2 to the k. For k equal to 1, 2, 3, and so on. And in between nk minus 1 and nk, I defined an to be constant. 1 over k squared times nk. K bigger than or equal to 1. If I put 1, you have 0, but it's okay. I can start from 0 here. 0, 1, 2, 3. So in very large gaps, an is fixed. It's given by this fixed number, but it's defined well in the following sense. I don't give all the details because they are simple calculations, but I invite to fill the gaps. The first thing is that the sum over n of an is finite. So it's more than big in H infinity. Indeed, it's in the Wiener algebra. So it's in L1. And second, and the way to do this is to break the sum into two sums. I mean, just as a hint. We can start from 2 to avoid difficulties at the very beginning. And this is the sum from k from 1 up to infinity of the indices which are between nk minus 1 and nk an. And for this, we have an explicit formula. Just plug it, very simple calculation. You'll see that it's like 1 over k squared, which is finite. And second one, to show that it's in the Dirichlet space, we have to calculate the Dirichlet integral. And this is the sum of n squared, precisely the same strategy as above. And this is even better. When you do this strategy and apply to the second series, it will be like the sum of 1 over k to the power 4. This one is 1 over k2. This is 1 over k4. And it's even, I mean, better conversion, but faster. So this one is also infinity. So 1 and 2 together show that f is in the Dirichlet space. Intersection, indeed, I mean, I write h infinity here, but you can replace h infinity even by the w, which is a notation for the Wiener algebra. I don't need this here, but I mean, h infinity is enough. So it's a very, very nice function. Good, but still, that's kind of half of the proof. I need to show that it's not a multiplier. How to show that it's not a multiplier? Well, to show that it's not a multiplier, I need, say, a function h in D such that when I do h times f, this is not in D. I need to find a good h. And this is again done by this definition. So definition, h of z is defined as the sum n bigger than or equal to 2. 1 over n log n to the power 3/4 z. The rest is a matter. I mean, the important part is to guess this h. The rest is a matter of calculation to show that it's in D, and when you multiply, it's not in D. it's, I mean, I leave it as an exercise for the student, but nothing delicate in that. The important part of the proof is to, I mean, think of these big gaps and define a function in the way I explained, and also to come up with the definition of a function such that when you multiply, it kicks out and go out of the space. And I mean, the rest, I leave it to you. So back to this diagram, mult D is really smaller than the intersection of D and H infinity. And I give you a little bit of more information about that, but still, even though we have a complete characterization by Steganga, which I will mention as the last theorem of our course, but still we'll see that it's not it's not a handy characterization. One characterization which in a sense is a reformulation of the problem and makes the connection to the Carlson measures and show the importance of the Carlson measure is this theorem. Let H be in D and mu measure mu a finite measure on D given by this formula. And D mu defined to be H prime. That's the prime makes the difference in Dirichlet spaces. H prime mod squared D a z, dA is dx dy, and divided by pi, it doesn't matter, it's just a normalization factor. So this is our measure defined via the function h, and then h is in the multiplier space or multiplier algebra of the Dirichlet space if and only if mu is a Carlson measure. This means, more explicitly, this means that H is bounded, or H is in H infinity, and there is a constant C such that integral over D mod f squared D mu is controlled by the norm of f in the Dirichlet space squared. And this is not Dirichlet space, that's the open unit disk. They are not the same. Maybe even I give less tail to it to make it distinct. So that's the definition of a Carlson measure for the Dirichlet space. Of course, it has to be bounded too. So we have a characterization for multipliers, and even though it sounds a bit strange, but I give the proof, and when you look at the proof, you see that, well, this is just a reformulation of the problem. It's not a solution to the problem, but still it's good, because then we go and seek which measures satisfy this property independent of thinking about multipliers. These are called the Carlson measures for the Dirichlet space. And a lot of people, a lot of prominent mathematicians have worked on this topic. And then based on that, we can even give a complete characterization of multipliers, even though it's not a handy characterization. The proof is easy. Let me give the proof. First, suppose that H is a multiplier. Then let F is in the Dirichlet space. And I mean, this formula that we see even in, I mean, maybe even high school, the formula for HF prime, H prime F plus HF prime, but let me write it this way. Let me write it as F H prime is equal to this minus minus HF prime. And then why I wrote it that way, because now the integral that we try to estimate is 1 over pi the integral over d mu was, I mean, the definition is here. D mu is mod h prime squared. So it will be mod f h prime squared and the area measure. And now I use this. I take the absolute value of both sides. And to take the square, I mean absolute value f h prime squared is less than or equal to 2. I keep prime. So I obtain from here. From here, I obtain integral over d mod f squared d mu is less than or equal to 2 over pi integral over d absolute value hf together prime squared dA plus 2 over pi integral over d h f prime squared dA. How's that? I know that h is bounded, so this h I can take it out, and this one, this integral is just the definition of the norm. So for this one, I have equal of 2y's. I write less than or equal, but for this part is just equality. 2y's the norm of HF in the Dirichlet score. Indeed, even for that one is less than because there is a constant term. So forget my comment. And for the other one, I write plus norm of H infinity squared. And what remains is majorized by the norm of F in T squared. So very rough estimation. And that's the point I use my assumption. My assumption was that H is a multiplier. So I use it here. I use it here. This is less than or equal to 2y's the norm of the multiplier squared times the norm of F squared plus the same thing. I factorize everything times normal FD squared. What remains for this calculation, it really doesn't matter. What matters is that from the beginning, we have the normal F squared with respect to d mu. And on the other side, there is a constant normal F in space d squared. This is what I wanted to show. One direction. So that's one direction done. And the other direction is pretty much the same thing. The argument is reversible. And this time I don't need to twist the formula. I really use the fact that HF prime is H prime F plus HF prime. And my assumption here is that this star holds. That's my assumption. And now, what can I say about D of HF? Well, by definition, it's 1 over pi integral over D HF prime point Z dAZ. And, well, I use this as before when I square it, and I have twice the square of the first one plus twice the square of the second one. So it will be less than or equal 2 over pi integral over d h prime f squared dA plus 2 over pi HF prime dAZ. And well, less than or equal for this one, I write it as 1 over pi h prime squared dAZ. I write it as integral over d f2 d mu. The whole thing is d mu. And for the other one more time, I use the fact that h is in h infinity. So twice norm of h infinity squared over pi integral over d f prime squared dA. And by assumption, the star formula, by assumption, this is less than or equal to 2, a constant normal f in d squared. And that's also d of f. So plus 2 norm h infinity squared normal f d squared. So which is, again, a constant times normal f d squared. So we are done. We are done because this says that df is less than constant times normal f. So it means that h is a multiplier.
I think you're missing an absolute value squared in the first line.
Yes. Thank you. Thank you. Yes, thank you. So h is a multiplier. And we are done. So as you see, there is nothing special about this theorem. It just makes a connection, bridge between two subjects. One of them is Carlson measures, this one. And the other is the multipliers. And now there is an independent study for characterizing the Carlson measure for the Dirichlet spaces. This is successful. And again, not something as easy as the Carlson measures for the Hardy space or even for the Bergman space. We have a very nice and beautiful characterization for those spaces. I mentioned them below. But for Dirichlet spaces is much more complicated, but it's still useful. Still, it helps in some results. So my concluding remarks is about Carlson measures. For this, we need to know what is a Carlson window or Carlson box. I'm sure you have seen many times, in particular in our focus program, in several talks, we saw the Carlson box. Here is the boundary arc I, and we go inside, and the way we go inside sometimes is equal to the length of I, sometimes length divided by 2 pi. It depends how we want to normalize. And this is called S of I. Well, Hardy. For Hardy spaces, that's a result of Carlson, and says that the measure is a Carlson measure if and only if the measure of this box is controlled by a constant, the length of the boundary arc. Very nice geometric characterization. And for the Bergman space, it's by Hastings, show that very similar, except that we need a square here. Two observations about this result, these two results. In each case, we have just one box, SY, just one box. And also on the other side, we have the Lebesgue measure. The Lebesgue measure is easy to handle. And now let's see what is the characterization by Steiger of the Carlson measures for the Dirichlet space. First difference is that you have to consider a finite number of the windows. I mean, not just one. Say one here, and so on. So I call this I1, I2, IN. And the second difference is that, so disjoint n disjoint boxes, and there is no restriction on n. That's the first thing. And the second is that the measure of the union of these boxes, measure of the union, the status one, k from 1 up to n, S of ik. This is controlled by a constant. Say I write A for the constant now, not to mix with what we have here, C, the capacity, logarithmic capacity of the union k from 1 up to n ik. So that's the second difference with the previous one. Instead of Lebesgue measure, we have here logarithmic capacity, which is another way to measure the length of sets, but it's a very difficult tool. difficult in the sense that the capacity is not additive. Here on the left side, of course, we can write some k from 1 up to n and mu of sik. That's okay because they are disjoint and we have a measure. We have this identity. But whoever just even don't think about it, some c of k from 1 to it's yeah, I mean, I even say absolutely not. Even for 2 arcs, the capacity of 1 arc, we know that it's asymptotically almost equal to 1 over log of its length. But even for 2, I1 union I2, even for this, we have difficulty and there are many, many technical problems. The distance between them is important. And it's a characterization by Steganga. It has been used in studying multipliers of the Dirichlet space, but this is difficult to handle. It's not an easy way to measure the bigness of, arcs on the boundary. Well, I think it's a good time to stop. And thank you all for bearing with me in this semester and following our courses. I really and profoundly thank each one of you. I hope you have enjoyed the lectures. Thank you.
Thank you for a brilliant set of talks. It was just absolutely terrific. Thank you.
Thank you indeed, Anatoly. Oh, everybody. And as we mentioned in the break, hope to see you all very soon in person.